So without further ado, Matthew Opala from Netguru, where he works as I understand, machine learning tech lead, right? So he's gonna talk to us about reproducible machine learning. So Matthew, over to you. All right, okay, microphone, of course. It's gonna be very helpful.
Yeah, thanks. Yeah, so thanks for the introduction. So, as Grzegorz said, I'm Mateusz and I work at Netguru, which is a software house, doing a lot of backend mobile, but also since a year ago, actually, machine learning. And today I'm going to talk about reproducibility because I believe it's a very important topic in machine learning and also in whole science. And machine learning has its own research flavor. So it's very close to machine learning. So let's start with the question, how many of you think that reproducibility is important in machine learning? Please raise your hand. Okay, so most of you. So I guess I don't have too many people to persuade, but let's try. So when you're doing science, and especially when you're doing machine learning, there are three properties of doing research that are desirable. So the first one is reproducibility, and let's define it as the ability to duplicate results of a prior study using the same materials, following the same procedures. And there is other thing called replicability, and it's similar, but the idea here is that we follow the same procedures, but not necessarily use the same data. So for example, reproducibility is just, we see some paper in the net, and that paper fortunately has a code base, so we just try to run it, and maybe it's going to work, and that's it. If we're doing replicability, then our machine learning algorithm, for example, needs to generalize to some new data. So for example, if we take SSD network for object detection, it works on several benchmark datasets. And the most desirable thing in doing research is generalizability. So our concepts, our results are generalizing, can be applied to different contexts. So you might guess probably, as I guessed some time ago, that first two are quite easy in machine learning, in software engineering, but the third one is difficult. But actually, there is already a problem with the reproducibility, and there is a reproducibility crisis in science. 3 years ago, there was a paper in Nature in which there were some surveys presented. So the authors asked questions to more than 1,500 researchers in several fields. It might be a bit biased because a lot of researchers were from medicine and chemistry, and their reproducibility is much harder than in machine learning. But the results, you might say, that are still terrifying because almost even more, yeah, exactly 80% of people, 90% of people think that there is significant crisis in reproducibility, and only 3% of those researchers said that there is no crisis. But there is actually a more terrifying question that they answered. So, have you failed to reproduce your own experiment? And about 70 people in chemistry says yes. So, experiments that cannot be reproduced even by the author of the paper have no significance to science, actually. And you can see that most of those bars are above 50%. So the question is, yeah, so this is madness, and it is very terrifying for science, but is it that same bad in machine learning? Maybe not as bad as in chemistry, but it's not great. And there are a lot of papers that lack code or pre-trained weights, and they are difficult to reproduce, and there are a lot of such threads on Reddit or other discussion forums when people are trying to reproduce some results, even from the top conference like CVPR, and they find some mistakes in papers. Papers went through that conference being validated without the code and weights, and somehow that conference should be a proof that the research is good, but it's not. So that's a huge problem. So what can you do when you read the paper and you cannot reproduce it? So one solution might be to email the authors. And actually, 7 years ago, I was trying to reproduce some results from the paper using deep autoencoders for semantic image hashing by Jeff Hinton, who is the father of modern deep learning. But even him didn't provide enough details to reproduce the results, and my restricted Boltzmann machine generated only random pixels, basically noise. So I emailed the co-author Alex Krzyzewski, and he responded to me some details, and especially that he didn't add noise to visible reconstruction, which was actually stated in the tutorial by Jeff Hinton, which was cited in that paper, so it was very misleading. But once he responded to me, it occurred that it can be reproduced. So there are many reasons why it's so difficult to reproduce science and especially reasons specific to machine learning. So the first one is that machine learning is a very fast evolving field. And you can notice that just by following on Twitter the most prominent data scientists or machine learning engineers, and every week we see like 5 up to 10 new generative adversarial net papers, and it's very difficult to follow. Even only one architecture like generative adversarial networks, it's very difficult to follow computer vision, and even more difficult to follow computer vision and, for example, natural language processing at the same time. So if you want to publish, and there are no actually so strict rules at that conferences, then you might just omit some details because you are pressed by time. The other thing, a lot of research is often funded by big commercial interests, so like Google, Facebook, Uber, and sometimes they release just training details but no model, like Deep Speech by Baidu. Sometimes they release only pre-trained models, and sometimes they skip training details and they do not release the model, like OpenAI with GPT-2. So that's another reason. The third reason is sometimes basically poor data scientists are doing data fishing and they're just choosing data points that are good for their hypothesis. And the last but not least, and I think the most important, is that in machine learning community, which is very research driven and a lot of people are coming from academia, we lack machine learning ops culture. That is, we don't use tools for data versioning, data managing, and experiments management. So basically, we lack the whole thing that we call DevOps that we lacked 10 years ago in software, in traditional software development in some manner. So what is machine learning ops? The dictionary definition is that it's practice of operationalizing and managing the life cycle of ML system in production. In my definition, in simple words, is basically that it's more like a culture of ethic of the professional machine learning engineer who owns its machine learning model since the beginning of development to the production. So basically, you train the model and you are able to reproduce the results, and if the model is good enough, you are able to quickly deploy that model to production, or even you are quickly able to check in production through some A/B testing, for example, whether the model you developed is in fact better in production than the previous model. So the classic machine learning pipeline looks like this. We have some input data, which might be from various sources. So from relational databases, from NoSQL databases, from distributed file systems and other stuff. And then we usually do some data processing, which starts with the cleaning, with tidying data, and then feature engineering. And then we train the models, evaluate them. And if they're good enough, we can deploy them. And we go again. And it's never-ending life cycle of machine learning model. And you can see that there are a lot of points here that are not specific machine learning code. And there was actually a paper in 2015 about hidden technical debt in machine learning systems that pointed out that in the production systems there is only a little of machine learning code, and all of above the machine learning code, like data collection, feature extraction, managing the experiments, data versioning, it's simply software engineering. And we should apply just typical software engineering best practices to maintain such machine learning systems. So if I didn't persuade you to store your experiments, to manage your experiments, maybe Boromir will do. But my question right now is, how many of you had that situation that you run some experiments, you thought that they are not really relevant, but after 1 week or 2 weeks, you wanted to go back to that experiment, and you didn't save, for example, hyperparameters. So did any one of you had that situation? I think it's like the first thing, when you're into machine learning, you're just trying out some machine learning algorithms with CLI. And basically, if you don't push to some repository each your experiments within one commit, then everything which you develop between commits and you run experiments between the commits is lost, because you just forget that you run something. And I'm doing that machine learning and reproducibility stuff since some time. And I think we are only at the beginning of our path at Netguru for achieving reproducibility in each project. Sometimes we are closer, sometimes we are further. But even some time ago, I had that issue that I ran some experiments that I thought they are not relevant. I didn't commit them. Basically, it was about training some neural networks on randomized labels. And I needed to train hundreds of those networks. And I wanted them to overfit to completely random labels, but all of them to the same labels. So in the first step, I randomized the labels, and I saved those labels somewhere and put those labels into all my experiments. And then at some point, I killed that machine, and I killed that randomization of labels. And in 2 months, my friend needs to reproduce that. And I don't have those labels because they're on some Google Cloud machine. So basically, I lost them, but I don't because of the nature of the task, because my networks actually remembered the labels for each training example, so I can just fit all the training examples through the network to get the exact labels. But generally, the case is, even if you think a lot about the reproducibility, it's still very easy to lose some information. And that's my motivation, that we should use tools that helps us to build that reproducible pipelines. So, and then the end goal for that reproducibility is actually continuous delivery in machine learning. So continuous delivery term was coined in 2009 by Jeff Humble, and he described it as ability to get all types of changes into production quickly, safely, and in sustainable way. And what kind of changes we have in machine learning development? So the first one is code. Code changes, but here we can apply the same things like in traditional software development. So we can use Git, Circle CI, or Travis, or Jenkins, whatever. But there are 2 new things, data and models. And we need some data versioning and some models management. So management for experiments, for training, for deployment. And today I will tell you how we address those 2 in Netguru. So the first is data management. And the author of the paper about hidden technical debt that I mentioned before said that if data replaces code in ML, and code should be tested, then it seems clear that some amount of testing should be applied also to the data. So we can draw that comparison. So in software engineering, we have several principles, like we version code. And the same thing we can do in data engineering or in machine learning. We can version data. In software engineering, we have clean and explicit interfaces between services. In data engineering, we can have also the clean and explicit interface between code, which is running on some data, and the data. In software engineering, we do unit testing and integration testing, and machine learning is still software engineering. So we can still do unit testing, and we can check data quality. We can do some schema checks. And the last thing, but not least, in software engineering, we have monitoring, and it's very important in machine learning, especially when some data changes with time. So we can detect some dataset regressions and basically the concept drift. So to tackle all those things, we use skill data. It's basically a library or portal, platform, whatever you want to call it, that is interfaced to AWS S3. It helps to share data at scale. We can use inline documentation through Jupyter Notebooks there. All our data is searchable through Elasticsearch. It provides immutable versions for datasets, and it's very important because it's very easy with Kilt to just throw the test set and make sure that all your experiments within all your team are testing the algorithms on the same test set. And they can still obviously gather more data for the training set, for example. And that way of managing and versioning data broadens the data access within an organization. Because there is no such thing like someone just downloaded some data, trained on the data, and never ever told anyone or wrote on one Slack channel which was private. So Qt is very simple to use. So the main entity in Qt is package, and package should be probably something like train set or validation set or the test set. And using the set function, set method, we can tell Qt which files we want to include in the package. We can also include with setdir whole directories. We can add some metadata which describes the data set. Also, we can add probably some MD5s for safety reasons. And at the end, we can push that to S3 very easily. And then all other team members can download that package, the same package, with one simple method and get access through Python code to that data. And the other thing I wanted to talk about is experiments management. So experiments management has several challenges. And as I said before, I think it's difficult to keep track of all experiments, to always save by hand all hyperparameters, all metrics you gathered during the training. And especially it's difficult to reproduce all the code. And it's very difficult to have that rigor that each commit is a separate experiment. So it would be nice to have some tool or library that somehow helps you to keep that rigor. There are no standard library agnostic ways of packing and deploying models. There are several that are tied to some bigger platforms or frameworks like Michelangelo from Uber. And those custom platforms like Michelangelo usually provide only limited number of algorithms, and it's somehow difficult to extend those. So there are platforms that has some advantages, drawbacks, and the good thing is that there are a lot of platforms already for reproducing, for reproducibility, for running machine learning experiments in a reproducible manner. And at Netguru we decided to use two. So the first one is Polyaxon, and Polyaxon is basically, his goal is to run reproducible experiments on top of Kubernetes. So you might say that it's competitor to Kubeflow. The author of Polyaxon says they're compatible. I don't really see the way they are compatible. I think they're competitors. And Polyaxon is great in managing those experiments, and being still quite young, it's growing in the community, and I think it's the next thing after Kubeflow. But there is this drawback of Polyaxon that it requires Kubernetes cluster. So if you just want to run some experiments on dedicated machine or locally, It's kind of overhead. So the other thing we use is MLflow. It's from Databricks. And MLflow focuses more on managing end-to-end machine learning lifecycle. From those two, I usually use MLflow, so I will tell more about MLflow. But for bigger projects, we use also Polyaxon. So in MLflow, we have three main components. The tracking component, which is responsible for saving hyperparameters, for gathering metrics, learning curves, and storing models. And also, it has UI, which can nicely show you how your model performs. And there are several use cases to use that UI. The typical one is to use it as a leaderboard, like in Kaggle, so you can compare your models, and you can even make it competitive within a team, so your team members compete like in Kaggle to get better model. Sometimes it might be a good idea, sometimes not the best, depends on the team, on the task. It also might be the use case that's MLflow UI to just monitor the production and how the models in production behave. The other component is MFO Projects. It's basically the format to organize the machine learning project. And the last component is ML models, MLflow models, which is basically the way of packaging machine learning models for deployment. So key concepts in tracking are, there are 5 key concepts in tracking. The first one is parameters. And those are usually hyperparameters of models. So if we train some neural networks, we usually choose some learning rate, maybe momentum, maybe optimizer. We can choose stochastic gradient descent or Adam. And those hyperparameters should be stored somewhere. So the first thing that MLflow is responsible is storing that hyperparameters. So we know, and we can see in the MLflow UI with which hyperparameters our models were trained, and we can easily reproduce those results with that hyperparameters. The other important thing are metrics. So usually we gather metrics like accuracy, precision, recall, and those metrics are very useful to compare different models. The third thing are artifacts. So the things that we save after the training or during the training, like learning curves or just logs about those metrics. So we can save data. So we have versions of data, and we can actually connect MLflow with Kilt and just save directly to Kilt to S3. We can save snapshots of models, so it might be very useful for early stopping. And the other two things are source. Source, it means which script we run, and the version, so which commit that is. So we are sure that what code exactly ran that experiment. And MLflow tracking is very simple. So we can open context manager in Python with start run function, and it opens experiment, and experiment collects a lot of runs. So it's one-to-many relation. An experiment, you can think like experiment is like competition in Kaggle, and runs are different runs within one competition. But also we can restrict experiment to just one algorithm and runs to different hyperparameter tuning or different feature engineering. And to log parameters, we just call logParam method. And in this case, we log alpha and L1 ratio. We can log easily metrics. And with log model, we save model to the ML model format, which is shared through different frameworks. And all of this helps us. All of this can be visualized in MLflow UI, which can be on local machine, or it can be deployed somewhere else. We can just set URI to where we deployed the MLflow UI. So the second component in MLflow is MLflow Project. And MLflow Project is a very simple format. Usually there are two YAML files. The YAML file called ML project describes how the project is, basically describes the project. So the name of project, entry points, so the commands that we can run within the project, and the project environment. In this case, we have second YAML file, conda YAML. This is typical conda YAML file that that collects all information about packages within the conda environment. But it could be Docker file also, and probably it's better, especially for productizing some machine learning. But in this simple example, we just use conda YAML. So how those files looks like? On the top, we have ML project YAML, and we have name of the project. We have conda env, so this is the name of our environment. And the third is entry point. So we have one entry point main. With CLI from MLflow, we can run that main, changing those parameters. And the command that we run is the script min-instance or board artifact. And we could have more those entry points like main run or something to different experiments, and project can have more experiments. So for example, if we do training of neural nets and then some clustering on feature maps, then we just have 2 entry points. And in the bottom we have sample conda YAML, which we can generate just from the conda env. And the last component in MLflow is MLflow model. It's a simple way of storing machine learning models. So we have a directory about the model that contains the information about the model. And the information is, again, in the YAML file called ML model. And the model itself, which is in the format that is suited for specific framework. So in case of scikit-learn, it's often Pickle, but probably not the safest way to save. But if we do, for example, Keras, then it might be HDF5. And the ML model contains the time when the model was created, the library, so sklearn, the path to the Pickle model, the version of the library, which is very important, and the name of the function, how to load that model. And that's basically all. And those are the main components of MLflow. And it's very simple to use and experiment, so I encourage you very much. So I'd like to sum up those points I mentioned today. So I think that achieving reproducibility is not trivial at the end, but it's very important, and it's we should aim for it. And there are already many tools that can help us. So MLflow, QData, and Polyaxon, those 3 we use at Netguru. But there are others that we want to evaluate, and maybe we will switch. So Kubeflow, Seldon.io, DVC, and probably many more. And the last thing I wanted to say, it's remember, ML engineering is still software engineering. So all best practices from software engineering applies to machine learning development. So that's it from me. Thank you very much. And here is my contact if you want to hit me. If you want to contact me, just hit the email, or you can grab a coffee with me later. Thanks.
Thanks, Matthew. I'm not sure whether you have Slido here on the browser. Yeah. We might just open up. There were a few questions. Okay, and they are sorted by the upvotes. So the first one, so obviously that was on your last slide. So you looked at some other tooling, right? Yeah. But maybe can you tell a bit more about why you haven't chosen those, or?
Yeah. So basically, Kubeflow is seems to be alternative to Polyaxon. So the definition was like there is no very important reason why I chose Polyaxon. I heard from my friend professor from university that Polyaxon is a great tool. So basically, it was friend recommendation. I look at DVC, heard good things, but DVC, my friend had many difficulties with connecting Qt with DVC, and we're already using Qt. So that's the reason I didn't look into DVC. But that's a plan for me for the future. So Basically, I started with MLflow because it seems to be the most simple to prototype quickly. And I'm doing a lot of prototyping and research recently, so that's my choice for MLflow. And Kill Data has that nice interface of using data that I like very much from Keras.
Cool. Okay. Just looking at the time, we still have a few minutes, so maybe let's just go through the rest as well.
Okay.
So data versioning in Quilt.
Yeah. So each package we create has the version that is just saved on S3. So I'm not sure what kind of details I should provide here, but yeah, basically each package we create has the version, and it's stored on S3.
Okay. And Google Cloud. Are you aware? Is there anything similar to?
Yeah. So So on Google Cloud we have buckets like at S3 the same way. The only problem is Kill doesn't support yet Google Cloud, but they plan to do. On the roadmap, I think the next thing they want to do is continuous delivery pipeline for data, and then supporting other clouds, which probably makes sense. And most of their customers is already on AWS. But you can easily build probably similar tool to Kilt. Maybe not all the features, but just to connect data in that Keras way. Using Google Cloud buckets, but I'm not aware of any wrapper around Google Cloud buckets.
Okay, and the last one probably is the Azure stuff, right?
Yeah, so I don't have experience with Azure stuff, but MLflow has direct deployment to Azure and SageMaker. So, for example, it doesn't have direct deployment to Google yet, but it works with Azure.
Okay. Cool. Thank you very much once again.
Thanks.